Hello and welcome in our study of linear algebra. Our topic for today is linear transformation. So let's consider any two vector spaces x and y. Okay. Then to each vector, okay, to each vector x. Okay, so when you have these two vector spaces x and y, okay, and we choose every or each vector in each of the vector spaces. So you choose x being a member of the vector space y. Then to each x we assign what a unique vector y. Okay. So then we say that a mapping of x onto into y is what is given. Okay. And such mapping is denoted by a capital letter. Okay. So to each vector x, okay, the image of this vector x is denoted by f of x being equal to y, where this f is the operator. Okay, is what is the operator, and it's also called a linear operator. Okay, so now for a vector space or for a map f to be a linear map, it have to satisfy two conditions. That's vector addition and scalar multiplication. Okay, so we choose two vectors, okay, v and x, such that f of v of x is given by f of v plus f of x. Okay, that's vector addition. And you also choose another scalar, c, which is which belongs to k. Okay, K is what? Is a field. When we say a field, is a commutative ring in which every non-zero element have an inverse. Okay, it have multiplicative inverse. This simply means that to every real number or to each scalar, you can multiply, you can divide, you can add, you can subtract, except division by zero. Okay, that's meaning of what scalar. Okay, meaning of a field. Okay, so from here we say that a linear map is what, or this map f of x maps onto y. It preserves vector addition and scalar multiplication. Okay, it preserves vector addition and scalar multiplication. So now let's look at some few examples. Okay, so now let's capital L be the operator defined by 3x. Okay, so when you have a vector, x such that x is two dimension, okay, so x can be x1, x2. Okay, then when you perform the operator on this vector x, you get what L of x being equal to 3x. Okay, so we can choose a field, a scalar alpha, such that when we multiply the scalar alpha by the vector x and perform the operator on the results, we get 3 alpha x. Okay, so from here we can factorize alpha out. So when we do that, we get alpha 3x. Okay, then we know that from definition our 3x is the same as L of x. Okay, that's scalar multiplication. I hope this is straightforward, right? So let's consider vector addition. So here we choose another vector y, such that y is also two dimension. Okay, so y can be y1, y2. Okay, so L of, from definition we know that L of x is 3x. Okay, so when we add another vector y to x, we have x plus y. Okay, and when we perform the operator L on it, we get L of x plus y, which is 3 times x plus y. Okay, so from here we can expand the bracket. When we do that, we have 3x plus 3y. Okay, and this is the same as L of x plus L of y. Okay, so therefore, since these have satisfied both conditions, then we see that L is what? A linear map. Okay, or L is a linear transformation. L is a linear map, or L is a linear transformation. Okay, so now let's move on to linear functionals. When we say linear functional in algebra, okay, or in vector space, a linear function actually maps a vector space to its scalar field. Okay, it maps a vector space to its scalar field. Okay, so now let's choose let's say v b, let's say two-dimensional vector of what? 2 dimension. Okay, then a map, let's say f, okay, such that there is a definition f of v is given by x squared plus xy. Okay, so this is the definition. Okay, so now you see this a vector. Okay, so let's choose any vector at all. Let's say our v, okay, being equal to 1 3. Okay, 1 3. So therefore, from this definition, f of v, or f of v is the same as f of 1 3 is given by x squared, that is 1 squared plus 1 times 3, which is 1 squared is 1, 1 times 3 is 3, so 1 plus 3 is what? 4. Okay, so the result is what? Is scalar. 1 3 is what? Is a vector. Okay, and f is what? A linear map. Okay, but since this operator, the operator f, have mapped a vector to a scalar, then we say that f is a linear functional. Okay, v is a vector, but when it's a vector which is defined by x squared plus xy, that's a vector of 2 dimensions, right? So when we substitute the elements in v, that's 1 3, into this operator, that's x squared plus xy, we have 4, and we know that 4 is what? Is scalar. Okay, so here we can make a conclusion that our f is what? A linear functional. Okay, so a linear functional maps a vector space to its scalar field. It maps a vector space to its scalar field. Okay, we also have another example here, right? So we have example 1. Okay, let me show the detailed solution. I think I have it. I have it here. Very good, very good. We let L be a linear map. Okay, that's this is a mapping that's transforming 2-dimensional vector to 1-dimensional vector. Okay, defined by this L of x being equal to, let me use this color. Okay, good. This is the definition. L of x is given by what? x1 plus x2. Okay, we are to show that L is a linear transformation, so we let x be equal to x1 x2, that's 2-dimensional what? Vector, right? And we are to transform it to 1-dimensional vector, right? So we choose another vector y, so that y is equal to y1 plus y1 y2, okay, and a scalar alpha. Okay, so therefore the sum of these two vectors is given by x1 plus y1. That's what we have here. then x2 plus y2. That's what we have here. But we know from definition that our L of x is given by the sum of the elements of in what? In x, right? So we have x1 plus x2, and therefore our L of y will be what? Y1 plus y2. Okay. So now let's consider vector addition. Let's consider vector addition. So our L of xy, our L of x plus y is given by L of x1 plus y1. That's this one. Okay. x2 plus y2. Okay, so this whole thing, x1 plus y1, will be what? Like our x from the in the definition, and the whole of this x2 plus y2 will be our x2. Okay, so therefore L of x plus y is given by x1 plus y1 plus x2 plus y2. Okay, now we can group them, right? We can group the x and the y's. Okay, so we have x1 plus x2 plus y1 plus y2. Okay, so this we have this x1 plus y2 plus y1 plus y2. Okay, but we know from definition that x1 plus x2 is what? L of x, and y1 plus y2 from here is what? L of y. Okay, that's what vector addition. Now let's choose a scalar alpha. Okay, we have alpha, and let's choose a vector x. Okay, so now we know that our vector x is x1, x2. Okay, so when we multiply alpha by x, we have alpha, then x1, x2. Okay, and this is the same as alpha x1, alpha x2. Okay, that's what we have here, right? So we have alpha x1, alpha x2. Okay, and from definition, L of x is x1 plus x2, right? So alpha x1 is more like L of that will be what? X1, and alpha x2 is just x2, right? So we find a sum. So when we do that, we have alpha x1 plus alpha x2. Okay, we can factorize alpha out. So when we do that, we have this. That's alpha x1 plus x2. And we know that x1 plus x2 is what? L of x. So we have what? Therefore, alpha x is given by alpha L of x. And hence, L is a linear transformation, right? Now let's solve a trial question. You can pause this video and try your hand on this question. Okay, it's very, very interesting question. Very good. This is the question. Yeah, let f be the mapping from two-dimensional vector to one-dimensional vector space, right? That is defined by this. That's f of xy equal to x plus y x. Show that f is a linear map. Okay, this is the question. You can pause the video and try your hand on this question. Okay, let's begin. So now we know that we are to show that f is a linear map. So f should satisfy what? Vector addition and scalar multiplication. Okay, so now let's choose two vectors. Okay, you see from the map we are transforming two-dimensional vector space to another two-dimensional vector space. Okay, so we choose our vector should be what? Two dimension. So we have vector u, that is ab, and vector v to be a prime b prime. Okay, and a scalar k. Is what? A real number, and it is also a field, right? So now let's find the sum of these two vectors. So we have u plus v. So you see, u is ab, v is a prime, b prime. So u plus v is given by a plus a prime, b plus b prime, right? So that's what we have here. So you have a plus a prime, b plus b prime. Okay. Then from definition, we know that f of xy is given by x plus y x. Okay. So we can apply it here. So f of u, where f is the operator, f of u is given by a plus b. So we find the sum of the elements in u. Okay. You see, from definition, we find the sum of x and y. That's xy, x plus y, then x. Okay. The same thing applies here. We have ab. So we have a plus b a. Okay, that's f of u. Then f of v, this is v, right? So our f of v will also do what? A prime plus b prime, then a prime. That's what we have here. Okay. So now let's look at the first condition. That's vector addition. Vector addition. So that's, we have two vectors. We are given two vectors, u and what? We chose two vectors, u and v, right? So the sum is u plus v. Then when we perform the operator f on it, we have f of u plus v. Okay. And this is the same as, we know that u plus v is what? U plus v is a plus a prime, b plus b prime. Okay. So that we can replace u plus v by this. Okay. So from definition, you see, a plus a prime is just like x, and b plus b prime is just like y. Okay. So we find the sum of x and y. So that's a plus a prime plus b prime. Okay. Then x. Okay. So this is more like x plus y x. Okay. X plus y x. Now we can group this into a plus b, a plus a prime plus b prime, then a plus a prime. Then we can break this one into two parts. That's a plus b a, then a prime plus b prime a prime. Okay. But we know that a plus b a is what? F of u. A plus b a is what? F of u. Okay. And a prime plus b prime a prime is f of v. Okay. So we are done with vector addition. Okay. It have the map f have what? Preserved vector addition. Okay. Now let's move on to the second condition. That's scalar multiplication. So we chose a scalar k. Okay, we chose our scalar k. Okay, this is our scalar. And now let's choose any vector. So let's select vector u. Okay, let's select vector u. So therefore, let's multiply scalar k by u. When we do that, we have ku. Okay, then we perform the operator f on it. So we have f of ku, and this is the same as, we see our u is given by ab. Okay, so therefore when we multiply the scalar k by u, we have k multiplied by ab, and this is the same as ka kb. Okay, that's what we have here. So we can replace ku by ka kb. Okay, and from definition, ka is the same as x and kb is what? Y, right? So we find the sum. Thus we have ka plus kb then k, that's x plus y, x. Okay. So from here, we can factorize k out. So when we do that, we get what? K multiplied by a plus ba. And we know that a plus ba is what? F of u. So therefore, f of ku is given by k f of u. And here we can say that scalar multiplication have also been preserved. And therefore, our operator f is what? It's a linear operator, or our map f is what? A linear map. Okay. Thank you so much. I'm Godfred Enchukodia, a graduate and teaching assistant at the Kwame University of Science and Technology, Department of Mathematics. Don't forget to share, subscribe, and like my YouTube channel. Thank you.